Hey everyone, welcome to This Explainer. Okay, take a deep breath. Today we're going to patiently build your physics toolkit so you can totally conquer kinematic equations and projectile motion for your upcoming exams. I know physics can sometimes feel like a daunting puzzle, but today I'm going to act as your personal tutor. We're going to take it slow, give you the real intuition behind the math, and break down these concepts so clearly that you'll feel completely confident on test day. Here's our roadmap for today. We're going to cover distance versus displacement, the kinematics equation toolkit, separating the x and y axes, trajectory types and formulas, using the quadratic formula, and wrap it all up with a problem-solving checklist. All right, let's jump right into part one, distance versus displacement. So imagine running around a track until you are right back exactly where you started. Intuitively, you feel tired, your legs are burning, but physics? Well, physics sees your journey a bit differently. As far as displacement is concerned, if your starting and ending points are the exact same, you literally haven't gone anywhere at all. Your displacement is a big fat zero. Take a second to compare these two on the screen. Distance is just adding up all your steps. It's a scalar quantity, meaning it's always positive and just measures the total ground you covered. Displacement, on the other hand, is a vector. It only cares about the shortest straight line path from your start to your finish. And because it actually cares about direction, it can be positive, negative, or, like we just saw, exactly zero. Let's look at a football analogy to really lock this in. If you pass football to a friend and they instantly kick it right back into your hands, the ball's total displacement is zero. It's right back where it started. But the total distance the ball traveled, that's actually double the physical space between you two. Moving right along to section 2, the kinematics equation toolkit. Now, notice how we categorize motion here. We've got uniform motion, which is just moving at a constant, steady speed, kind of like a car cruising down an empty highway. But things get a lot more interesting with non-uniform motion. That's where acceleration comes into play, like a scooter gunning it at a green light. And when velocity changes like that, we need a specific set of mathematical tools. Okay, deep breath. Look at these three primary equations. If you're dealing with constant acceleration, these are literally the only tools you need in your belt. You've got one for final velocity using time, one for final velocity squared using displacement, and one to find total displacement. Seriously, memorizing just these three will get you through almost any constant acceleration problem you'll face. All right, on to section 3, separating x and y axes. Before we split things up, we really need to remember what a vector actually is. Because velocity is a physical quantity with both a magnitude and a direction, we have this amazing power to break a complex, diagonal launch into two much simpler straight-line motions. Think of the horizontal x-axis as a perfectly smooth river flowing at a steady rate. If you drop a piece of wood in it, it just glides along at a constant speed, right? There's zero acceleration pushing it forward or backward. Meanwhile, the vertical y-axis is totally controlled by gravity. It's constantly pulling down at 9.8 meters per second squared. It's like sitting in a moving train and tossing a ball straight up. The ball comes right back down to your hand because its horizontal speed matches the train. It's perfectly independent from its vertical trip up and down. So let's see how this builds your exam strategy. Whenever you see a projectile launched at an angle, let's call it theta, your absolute first instinct should be to use trigonometry to split that main velocity vector. You use cosine to find your constant horizontal speed, Vx, and you use sine to find your initial vertical speed, Vy. Actually, write this down in big bold letters in your notes right now. Vx never, ever changes during the flight. Never. Okay, that brings us to section 4, trajectory types and formulas. First up is the horizontal cliff launch. Just imagine a ball rolling right off the edge of a flat table. Because it wasn't launched upward or downward, its initial vertical velocity is exactly zero. This makes your math so incredibly easy. You just use the y-axis height to find your total time in the air, and then you multiply that time by your constant horizontal speed to find out exactly how far away it lands. The second type is a ground launch. Think of kicking a soccer ball right off the grass. What's really beautiful here is the symmetry. The parabolic trajectory is perfectly symmetrical, which means it takes the exact same amount of time to reach its peak height as it does to fall right back down to the ground. Because of that, you can use these super clean derived formulas specifically for this shape to easily find your time, max height, and total range. Now, the third, and definitely the most complex trajectory, is launching at an angle off a cliff. Here, the path is completely asymmetrical. The ball goes up, comes back down to the level of the cliff, but then it just keeps falling all the way down to the ground below. Since it's not symmetrical, we have to be way more careful with our calculations. We absolutely cannot just find the time to the peak and double it. That won't work here.
Which leads us perfectly into section 5, using the quadratic formula.
Now, you might be dreading this part, but the real question is, when do you actually need to use the quadratic formula? Well, the answer is specifically for that third trajectory type we just talked about. You need it for the asymmetrical cliff angle launch, simply because your initial starting height and your final landing height are different. Hey, don't panic, just follow the process. By setting your final ground position to 0 and your initial position to the exact height of the cliff, you automatically create a standard quadratic equation. From there, it's really just plugging your variables into the classic -b plus or minus the square root formula. You're basically just letting the math do all the heavy lifting to find the time, t. But before you calculate anything, I want to give you a massive tutor tip. Seriously, as a tutor, the most common mistake I see isn't failing to understand the calculus or the core concepts. It's a simple sign error. Always, always double-check your directions. If your initial upward launch is a positive number, then gravity, which pulls downward, absolutely must be entered as -9.8. All right, final stretch, section 6, physics problem-solving checklist. When that inevitable panic sets in during an exam, I want you to fall back on this simple 4-step process to ground yourself. First, just list out all your known variables. Second, decompose your vectors to separate pure x and pure y axes. Third, pick the equation that fits from your toolkit. And fourth, do a final check of your positive and negative signs. Systematic problem solving is truly your best friend here. I highly, highly recommend you take a screenshot of this summary table for your notes right now. Committing these 3 specific formulas to memory for symmetrical ground launches will save you so much precious time during your final calculations, letting you completely bypass those longer derivations. So, we've built your toolkit from the ground up today. Remember, physics is really just a puzzle made of separated parts. So take a breath, trust your toolkit, check those signs, and ask yourself, when you face that blank page on exam day, will you remember the golden rule that horizontal velocity never, ever changes? Thank you so much for joining me for this explainer. Keep practicing, and I'll see you next time.